There's a bunch of bags on my floor. Again. It's time to perform the ritual of picking them all up and placing them in a single bag. We all have this guy in our house, right? A bag filled with bags, just bags all the way down. Once a carrier of groceries or lunch, each bag is now on its way to become a memory. They may look the same, but each bag is special in its own way. The anatomy of the stuffing of a bag varies house by house. It might be an outer bag with everything else dumped in. Someone might prefer the Russian doll approach of a bag in a bag in a bag and so on. Or your computer science aesthetic sense wants to make sure that each bag contains at most two bags. Well, it's all on you. My curiosity was piqued when I noticed that I was making a decision at every step on how to put the bags in. There are so many ways to stuff bags in one bag, but how many exactly? Before we start counting, I want you to keep two things in your mind. One, that each bag is special, and two, trees are pretty cool. If I put the red bag in the yellow bag, then I draw an arrow from the yellow bag to the red one. The tail of this arrow touches the container, and the head touches the containee. If I make all of these arrows between the bags depending on who is containing whom, I get what in graph theory is called a tree. And it looks like one, right? If I'm handed a stuffed bag and I peel it off one by one, I can make a tree corresponding to it. And while you're here, why don't you go pay a visit to your bag of bags and figure out what its tree is? I'm not going anywhere. To make this picture easier to read, I will represent a bag by a dot. And because each bag is different and special and sentient, I'll give it a special number. Now we have an honest graph theoretic tree. We call this outer bag a root, and because every bag has a different label, we call this tree a rooted label tree. So, how many rooted label trees on n vertices are there? The proof I'm about to present is from something known as the book. The book is a collection of proofs which are all basically connected by a theme that if the god of mathematics themselves were to write a proof, it would be this proof. More pragmatically, it's a collection of slick and lovely proofs. It's actually not that different from finding a speedrunning exploit. Such math proofs are like short poems with those hard-hitting lines. So let me recite one for you. Let us denote the number of rooted label trees by t sub n. If I want to make such a tree, I can proceed in multiple ways. Take this simple example. If I want to put 3 in 2 in 1, I can first put 2 in 1 and then put 3 in 2. Or I could have started by putting a 3 in 2 and then decided to shove a 2 inside 1. These two are different ways to achieve the same configuration. And if you don't record the process, you can't tell the order by looking at the final product. So let's record it. We mark the arrow that came first by 1 and the stuffing that was performed later by 2. This gives us these two ways in this example. In general, I want you to convince yourself that each tree which has n dots has n minus 1 arrows. Go ahead, draw it out. I'll be waiting here. If you have convinced yourself, notice this. We start with a rooted label tree from the get-go and we want to order the arrows. We can make the first arrow in n minus 1 ways, then we can pick the second one in n minus 2 ways, then in n minus 3, and so on. So, each rooted label tree can be made in n minus 1 times n minus 2, and so on until there's only one way left. We call this product n minus 1 factorial. This means that there are t sub n times n minus 1 factorial trees where we label the arrows in the order that they occur. If you were to record yourself stuffing the bag, there would be these many distinct recordings. This proof uses a method called double counting. As the name suggests, we count the same thing in two ways. So, how else would you construct such trees? Well, don't start with the arrows. Each dot, except the root, can have exactly one arrow going into it. To see this, think that each bag is directly contained in exactly one bag, but it can directly contain as many bags as it wants. To make an arrow, we pick the container bag in n ways and a bag to put inside of it in n minus 1. Now to put the next arrow, we select the container in n ways again, but now we have only n minus 2 target locations. We continue doing this process n minus 1 times until we have n selections for the container, but only one for the containee. Multiplying all of these ways gives us n to the n minus 1 times n minus 1 factorial. All that is left is to take both of the expressions together and stare them down until they divulge the truth. So we get that t sub n is n to the n minus 1. And the number of ways you can stuff n bags into one bag is n to the n minus 1. For 10 bags, this number is a billion, and it becomes pretty big pretty quick. With so many possible ways, it's likely that the configuration of the bag of bags in your house has happened for the first time ever in history. If that's what you wanted to hear today, well, I'm glad I could help. I've added some discussion and some points in the description below, and if you can leave a comment and share this video, it would really help me out. So with that, I will leave you with a silly little outro song that I made. My kitchen floor is a mess, a bunch of bags lying around. Gotta clean all of it up. There is a way I found that works, but it's a drag. I put a bag in a bag. Bag in a 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 bag bag in a 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 bag. How many ways are there? You gotta count all the trees, fix a route, label everything, that's all you need. Count all the edges, and then when you are done, n bags littering the floor, stacked up neatly in n to the n minus 1.